Next up, we have Dr. Michael Biercuk. He is going to give a presentation on making quantum technology useful. What? For enterprise and government. I can't wait. Dr. Biercuk has a very long history, and I can't bring up everything, but he is the CEO and founder of Q-CTRL and a professor of quantum physics and quantum technology at the University of Sydney, where he also serves as the Chief Investigator in the ARC, Center of Excellence for Engineered Quantum Systems. He's got a lot more that he does. Please check your bios for him. Dr. Biercuk, thank you.
Thank you. Thanks. It's a pleasure to be here. I was actually particularly enthusiastic when I saw the draft schedule that we were right after our partners, Quantum Machines. I think you're going to see a lot of complementarity in the talk. You're going to see how what we do connects to what QM does, but more importantly, you're going to see at a very high level what is really the state of the art in the field, what is happening, what is coming very rapidly, and then the way that we are helping to advance the field through infrastructure software. So if you're not familiar with Q-CTRL, what we do is build AI-powered infrastructure software to make quantum hardware useful. Our role is to bridge the gap between the low-level physical infrastructure, the devices that are made by the quantum processor manufacturers like IBM, and Quera and others, the physical controllers made by quantum machines, and then the high-level abstractions that people ultimately use to write algorithms that run on quantum computers. We provide everything in the middle. We provide that connecting glue, with a particular emphasis on a problem I'm going to come back to in some detail, which relates to error in quantum computers. So if you're not very familiar with that, I'll give you some insights in a minute. As just the highest level overview, the company was founded in 2017. We now have well over 100 staff members around the world in Australia, the US, the UK, and Germany. We are very broadly serving customers across different sectors. We have over 10,000 users of our software in its various forms. We work with governments worldwide. We work with enterprise users. We work with consultancies, academic research groups, national labs. We have a very diverse range of users. And the reason that we have that kind of penetration is that there is a shared challenge. And the shared challenge, if you've not encountered this before, is that quantum computing hardware is very different than classical hardware. If you're used to running things on AWS or on your laptop, the hardware just works. But by contrast, in quantum computing, the hardware is exceptionally fragile. It's very unstable. And so if you encode information into a quantum system, over time, that information gets randomized. The randomization of that hardware, this is a phenomenon for those of you who encountered this before, is called decoherence or error. It simply leads quantum computers to fail. So here is the dirty secret. Some of you may have heard about this. You may have heard about errors in quantum computers. The dirty secret is that when you, as a user, go and try to do something on quantum computing hardware, it fails much more often than it succeeds. You typically get the incorrect answer. So this is a very, very simple example. This is running an algorithm called Grover's search. It's a needle in a haystack type problem. What you expect is on the top. You should get the location of your hidden needle identified by the machine. That's the tall bar. But what you actually get, and these are real data from a real quantum computer that's commercially available, is the graph on the bottom. The correct answer is not identified by the machine. It's not even in the top 5 most likely outcomes according to this calculation. This is the typical user experience across all the platform vendors. What we've effectively been stuck with is wandering around in the dark. We're all trying to gain insight from quantum computers. We're trying to understand what is it good for, what can it do for me, what is the state of the art, and we just cannot get that insight. And so what we built and launched last year was a product called Fire Opal to help you see the light in the dark. Now, I'm not going to do like a heavy media press on what the product is, but I want to emphasize what it does and how it helps make quantum technology more useful. Now, the idea was to abstract away all of the details of that infrastructure software that we're producing such that an end user is not burdened with having to write tens of thousands of lines of code and focusing on the concepts of quantum control engineering, in which my academic team has worked for so many years. We build infrastructure software that allows for the full abstraction of the underlying hardware. You as a user only need to worry about the algorithm that you want to run, the problem that you want to solve, instead of worrying about how do I make it give me a useful answer? How do I add something called error suppression or error mitigation? How do I take care of readout errors? All of that is abstracted away with this tool. We've been very happy to work with a number of users in industry, but we're also excited that this is now being connected through some of our other partners in the ecosystem, partners who focus on solving problems in collaboration with enterprise and government users. Teams like our friends at Classic, QBraid, QCentroid, Strangeworks, and others. This tool, FireOpal, the infrastructure software, is becoming accessible through those front ends as well. Again, the idea is to make it very easy for you to actually get useful outputs without doing any of the work that a quantum physicist does or a quantum information scientist does. The idea is that there are no settings. There are no selections to make. There is no code to execute other than one command called fireopal.execute, and all you get at the end is better performance. I'm sorry that looks like the slide got messed up in the translation to a PC, but I'm very excited that in just a couple of months, this software will run natively within IBM quantum computers. So you can come to it via our product, via our partners at Classic and others, or you can just go to IBM. It is integrated, and there are some others that are coming in the announceables in the next 12 months, so please keep an eye open for this. What does it do? It gives huge transformational benefits, and I appreciate that some of the numbers on this slide look ridiculous. I get that, but this is all validated in the peer-reviewed technical literature. For those of you who are algorithm developers who have tried to run things on quantum computers, more than an order of magnitude improvement in something called the circuit depth, how complicated an algorithm you can run. Over 100x improvement in cost. It costs less to use this software because you don't have to run over and over and over and over again in order to try and average away errors. We have demonstrated up to 9,000 times improvement in the likelihood that a machine gives you the right answer. So what does that actually look like for the user? Remember the motif I showed you before of what you expect, what you actually get. These are real data. This happens to be from IBM, but we've seen this on a wide variety of backends. With that one line of code, you just get the right answer. It is a binary transformation from wrong to right. But to be just a bit more quantitative about this, we've shown, again, through, in this case, our partnership with IBM, that we can take some of the bigger devices that are available. Here, a 27-qubit device. We can use all 27 qubits on the device, and we can give you the correct answer to an algorithm with 99% confidence in just 400 executions. Now, for those of you for whom that's not familiar technically, it's a very, very small number of executions. And the contrast is that without this software, in 32,000 attempts, you never once get the right answer. 99% confidence of the right answer in 400 executions or never. That is the binary transformation. This is sustained across a wide variety of algorithms. So I'm not going to belabor this, but this is not a one and done. It's not a once-off. It's very broad. And so we started looking in detail at what are the applications that are most likely to deliver quantum advantage. And I will warn you that the next slide is the one you probably want to take photographs of, although I can already see in the preview it has been utterly destroyed by this PC and its layout. Scheduling and optimization is a set of problems where we see a great opportunity for near-term quantum advantage. And in particular, we've looked at different architectures across different platforms, superconducting, trapped ion, Rydberg atom computers. And the important idea is that in 3 to 5 years, with a 0x factor in size enhancement, that means systems no bigger than we have today, we believe that quantum advantage is actually achievable. The only thing that has to happen is the hardware needs to perform better, about 20x increase in what's called the circuit depth. And we're already on the way there in collaboration with our hardware partners. In order to make that more useful, we actually began engaging with single command execution at the hybrid algorithm level so you can run optimization problems. You don't have to worry about all the details of how you even design a quantum algorithm. The idea is you should not think about what a quantum circuit is. You should just run, and it should just work. Now, we put this out about 6 months ago, and we showed that running an algorithm called QAOA, very commonly used in the community, with one line of code, solve QAOA, everything is configured, and what you see is the contrast in the top, what you expect, and then alternating on the bottom, what you actually get with Q-control and what you get without it. And you see that it goes from a random distribution to actually the correct answer. So all of this together is part of what some analysts have called frictionless quantum software. The idea is to make this easy for enterprises and governments to access, leveraging the skills that they already have. And it is an important part of our effort to build what we call the software-defined quantum data center, leveraging what's been done by VMware and, oh, I don't know what's happening there. Leveraging what's happening or happened with VMware, giving the glue between all these different modalities in compute, whether it's GPU or CPU, things that are controlled by quantum machines controllers, all of that is connected to boost performance and utility via the infrastructure software that we build, enabling abstraction, which we know is key for the future. Just to close out here, I want to say that a lot of the same challenges actually carry over into another domain that's relevant to government called quantum sensing. The hardware is unstable. And we've been very excited that all the infrastructure software we've developed has been applicable to a new generation of quantum sensors as well. And this work was featured, we were featured in the New York Times just a couple of weeks ago for the work we've been doing in support of the AUKUS trilateral agreement, making quantum sensors useful for navigation applications in military applications. So if you'd like to hear more about that or any of the work that we've done in infrastructure software, please scan this QR code. I'm so excited to see so many cameras pop up. You'll also find my email there, so please get in touch. So thanks very much. Appreciate your time. We have time for any questions? You tell me.
Two questions.
All right.
Two quick questions. Let's do it.
All right, sir.
The very first one is quite simple. To say that soon it will be natively available with IBM.
Yes.
So I'm assuming that IBM will just get rid of all their efforts they've been doing in error mitigation.
I don't work for IBM, so I will suggest you contact them about that. Technically, we focus on something that's quite complementary to error mitigation. We focus on something called error suppression, which is at the lowest levels of the device, build a little bit of a, in cartoonish language, a force field around the individual devices to suppress errors. Now, this happens at the machine language, it happens at the compiler level, all these different areas. There's no post-processing. So you can combine what we do with error mitigation, which is a post-processing type technique, in order to simplify the overhead for error mitigation. Same thing with quantum error correction. We have shown in the technical literature that you can make quantum error correction better able to identify the errors in your hardware by combining it with what we do. So I think it's complementary more than a replacement.
And it will really be like, I go on IBM machines and I can use...
Performance management equals Q-control. Everything else is done.
And do you plan to do it also with IQ as well?
As I said, please look forward to many more integrations coming in the next month.
Thank you.
One last question.
This was probably on the slide that was PC messed up, but the different modalities for quantum computing have different error landscapes.
Yep.
Super empty qubits are more prone to errors than trapped ions, for example. Your solutions provide, are they more useful for certain modalities than others? Can you maybe just comment on that a little bit?
Yeah, so I really regret that the slide is so destroyed. Thank you, Microsoft. The idea that the hardware is very different is absolutely correct, right? And so a key part of what we do is we configure in the background our very complicated tool set to address the dominant error modalities in each of those systems. So I think the key message here is it's in bottlenecks. T1 in superconducting qubits, the incoherent error lifetime, like that's the biggest limit. And we need that to continue enhancing. On the other side, with some of the neutral atom and the trapped ion experiments, the challenges are more architectural, that you can show that the compilers get really slow when you start to go to bigger systems. So, there are different challenges that each one faces.
Your solution for the different modalities to provide the most value?
We configure it in the background, and a key part of what we do is we homogenize performance across systems. We have shown that we can take a trapped ion machine and a superconducting machine, and we can make them give outputs both at the 90% fidelity level, even though they have a 400x difference in cost to access.
Thank you. Hopefully Dr. Biercuk will be available later if you have follow-up questions or would like to get into a more engaged conversation. Thank you again. All right, we're going to